Okay, so in this video we will see some Laplace and inverse Laplace transform of some functions. We first use any random function and then we will see the Laplace and inverse Laplace transform of delta function and step function. So let's start. So first of all, we have to define some symbols using this sims function, and we will need two symbol variable. One is t and another is s for time and s domain. Okay, so now we have to make a function. So let's say I choose a random function. One is exponential minus 2 into t and then multiplied by sine tan t. So this is a random function in time domain. So now we have to transform this function into s domain. That means we want to apply a Laplace transform here, and to do this we have a built-in Laplace function Laplace, and put here f as you want to transform it, and as it is in time domain, so write here t, and you want to apply it in the s domain, so write here s, and whatever the output is, put it in another domain, let's say capital F. So now if you run this portion, you will see that you have obtained the Laplace transform of this, and you see this function is a function of s. If you put here some another thing, let's say it is d, so you have to also put here d, then you will see that instead of s you will obtain a d here. Okay, so let me write s again. Okay, so now if you want to do an inverse Laplace transform, let's say you want to do an inverse Laplace transform, so we have another built-in function here which is I for inverse Laplace, then write here capital F, then as this capital F is a function of s, so write here s, and you want to transform it into time domain, so write here t, and whatever the value is, let's say we want to put it in f2, another symbolic variable. One reminder that this t and s is not the regular variable. You see, these are two symbolic variables. That means you can treat it as symbols. So if you run this portion, you see you have the inverse Laplace transform which is equal to this thing. Well, so now let's do the Laplace and inverse Laplace transform of delta function. So to do this, we have to use a Dirac function and write here t. So this is actually the delta function, and we know the Laplace transform of delta is equal to 1. So let's see. So you see the Laplace transform of delta is equal to 1. So you can also do an inverse Laplace transform here, you will get the same thing again. Well, so we know that the Dirac function, the delta function has a spike at t is equal to 0, but if you want to get the spike at t is equal to, that means you want to get delta t minus 2. So this is simple, right? You just have to write here t minus 2. So now if you write this, run this portion, you see you obtain the Laplace transform exponent e to the power minus 2s. We know that if you shift 2 in the time domain, you have to multiply by e to the power minus 2s, right? And you can apply the inverse Laplace transform and you will get the same thing again. Okay, so now the part, now let's do the Laplace transform of u. So we know the Laplace transform of u is 1 by s, right? So let's prove it. Let's do the same thing in MATLAB. So to do this, we have to use a Heaviside function. Heaviside, we have a built-in function Heaviside, so let's use that. So Heaviside, well, so this is the Heaviside function, and write here t. So this will act like a like ut, but here is a problem. If you right click here and click open, you will see the description of this Heaviside. So Heaviside is, you see the inside the bracket you have x, and this Heaviside is equal to 0 for x is less than 0, and it is equal to 1 for positive x, right? Oh, sorry, for positive x, right? Well, so what does that mean? We know that step function looks like this. So this is a step function. Now the Heaviside function is telling me that, now Heaviside is telling me that when this is actually x, so when x is negative, the Heaviside's value is also negative, but when x is positive, this is equal to 1. Well, no problem here, but the second line is telling that the value Heaviside when x is equal to 0 or t is equal to 0, whatever you want, by default this value is 0.5. that means when x is equal to 0, here the value is 0.5. that means this Heaviside function looks like this. But no, we don't want this thing. We want that at x or t, whatever you want, when x is equal to 0, the function will be is equal to 1. So we don't want 0.5. Instead of 5 we want 1. So what to do? So what we have to do, we have to just copy this thing. Let's copy this thing and go back to your MATLAB file and paste it here, and you see Heaviside at origin. So what will be the value at the origin? By default it was 0.5, but no, you want actually at origin the value should be equal to 1. Well, so now if you run this simulation, so run this portion, you see the inverse Laplace transform is, so Laplace transform of step function is 1 by s, and if you again do a inverse Laplace transform, you will see if you do a inverse Laplace transform, wait a minute. Well, so this is giving the value here, inverse Laplace transform is 1. Well, so now let's shift this thing. Let's say instead of u, let's take it here. That means this is actually t minus 2. So let's put here t minus 2, and if you transform it, you see 1 e to the power minus 2s is multiplied with 1 by s, and if you again take an inverse Laplace of here, you see you get u, this Heaviside is actually u, so u t minus 2.